Hi, in this video we are going to see a summary of signals and systems. In fact, it will be a very brief but effective summary of what is expected, for example, in a textbook on signals and systems or in a course on signals and systems. So in general, our starting point is a signal, x of t, but let us also assume that x of t is Fourier transformable. That means its Fourier transform exists. So we have the pair x of t and x of omega. So the first question is, how can we represent x of t? By the term representation, we mean how can we express x of t as a superposition of simpler functions or simpler signals? Okay, this is our first question. And the second question is, if we apply x of t as the input signal of a linear time invariant system with impulse response h of t, okay, so this is our LTI system. And let us assume that this is a stable LTI system because we have to deal with the system action in terms of Fourier transforms. For this, we need stability. And our input is x of t. Our output will be y of t. And in addition, we have the information of the impulse response h of t of the stable LTI system. Now, a very short summary of what we do in a textbook, for example, the content of a textbook on signals and systems. We have to try to answer these two questions. The first question is, how do we represent x of t? So let us write it as question 1. How do we represent x of t, an arbitrary signal? And question 2 is, how can we calculate y of t, the output of the system, when x of t, the signal of interest, is applied as the input signal of this system. Now, these two questions are answered in two different ways, and these two different approaches are in fact identical to each other in a certain sense, but we use different concepts in the two different answers given to these two questions. Now, in the first case, x of t is represented in terms of a superposition of shifted impulses. So from minus infinity to plus infinity, x of tau, delta of t minus tau, integrated with respect to tau. So x of t is represented as a superposition of impulses. But what is an impulse? An impulse, in fact, is a zero duration signal. And since it is a zero duration signal, its Fourier transform has infinite bandwidth. Okay? So this point is very important as a superposition of zero duration or infinite bandwidth that means the Fourier transform, is non-zero over the entire frequency range from minus infinity to plus infinity, infinite bandwidth, shifted impulses. Okay, this is one representation that we use very frequently in signal theory. The other representation is x of t is equal to 1 over 2 pi from minus infinity to plus infinity x of omega e to j omega t integrated with respect to omega. This is in fact the inverse Fourier transform expression or the synthesis equation in Fourier transform. So x of t here is represented as a superposition of now infinite duration and zero bandwidth complex exponential signals. You see the duality between these two representations. So here x of t is represented as a superposition of now e to j omega t is the complex exponential signal with frequency omega. It is non-zero over the entire time domain, t from minus infinity to plus infinity. Therefore, it is infinite duration or zero bandwidth. Okay. Infinite duration or zero bandwidth complex exponential signals. Now, in the first representation with shifted impulses, we integrate over time. Here we integrate over frequency. Okay, so these are the two very frequently used representations, signal representations. One of them is the representation of the signal in terms of shifted impulses as a superposition of shifted impulses, and the second is a superposition of complex exponential signals. Okay, so these are the signal representations. So what about the second question? How do we calculate y of t? Now, to calculate y of t, we do the following. In the first case, the impulse gives us the impulse response. The weighted impulse, x of tau, first time shift. Delta of t minus tau gives us h of t minus tau at the output because of time invariance, and x of tau, delta of t minus tau gives us x of tau, h of t minus tau by linearity. And again by linearity, because integration is a linear operation, from minus infinity to plus infinity, x of tau, delta of t minus tau, integrated with respect to tau, gives us from minus infinity to plus infinity, x of tau, h of t minus tau, integrated with respect to tau. Well, we already know that this is x of t, so this is y of t, therefore. So we answer the question in a very simple and elegant way. Now, in the second case, when our signal is represented as a superposition of complex exponential signals, how do we evaluate the output if x of t is the input of our LTI system, which is also stable? Now, we use the fact that e to j omega t is the eigenfunction of an LTI system. Our LTI system, which is stable because we want the frequency response to exist. And here the output is h of omega e to j omega t. Okay? This is the result known as the fact that e to j omega t is an eigenfunction of stable LTI systems. Okay. Again, by linearity, if e to j omega t gives us h of omega e to j omega t, then if we use the weight x of omega e to j omega t, the system action will yield x of omega by linearity, x of omega h of omega e to j omega t. And then if we integrate from minus infinity to plus infinity with the factor appearing in the inverse Fourier transform expression 1 over 2 pi, x of omega e to j omega t, and we are integrating with respect to omega, so we are changing the frequency, in other words. The output will correspond to the expression 1 over 2 pi from minus infinity to plus infinity, h of omega, rather x of omega first, h of omega, e to j omega t integrated with respect to omega. Now again, we know that this is x of t, therefore this expression must be y of t. So y of t turns out to be the inverse Fourier transform of x of omega, h of omega. Okay? So, we get another very elegant result, but now here our representation of the input signal is in terms of complex exponential signals with the frequency range from minus infinity to plus infinity. So we use the synthesis equation of the Fourier transform and obtain y of t by using the fact that the complex exponential signal e to j omega t is an eigenfunction of a stable LTI system. So the first case, that means the representation in terms of shifted impulses, leads us to convolution. The output of an LTI system is the convolution of x of t with the impulse response. The second approach, that means the representation in terms of complex exponential signals, superposition of complex exponential signals, leads us to the expression, again, equivalent to convolution, because we know that multiplication of x of omega with h of omega in time domain corresponds to convolution of x of t with h of t. So I hope I have summarized the content of a course on signals and systems. In a nutshell, a very brief summary, but what we are essentially doing in signal theory or in the theory of linear time invariant systems is using either the first representation in terms of shifted impulses or the second representation in terms of a superposition of complex exponential signals. Okay, thanks for watching.